All right, guys, welcome back. This is going to be the beginning of Chapter 7. And what Chapter 7 talks about is solving systems of equations. In Chapter 3, we first really in Chapter 2, Chapter 3 was inequalities. Chapter 2, we introduced equations. Chapter 6, we spent creating linear equations. Now we're going to solve systems of equations here in Chapter 7. So what I want you to do to start is you're going to be doing a lot of pausing the video, solving problems, then comparing your answers to mine. So just to get your brain kind of into math mode, I want you to go ahead and graph the following equations. Graph them both on the coordinate plane, and this should be review from Chapter 6. So go ahead, pause the video, graph both of these linear equations on the same coordinate plane, and then tell me write down what you notice. Okay, so hopefully you have done that. You have now unpaused the video. These equations are both in, as you may hopefully know, slope-intercept form. So what do? Well, we graph the intercept, then we use rise over run for the slope. So for 2x minus 3, I'm going to put a dot at minus 3. Then I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. And I'm going to go ahead and draw my line through it. I like using different colors in this lesson. I think it makes things more apparent. So what we're going to do now is graph our other one. And we're going to put a dot at minus 1. This one has a slope of 1. So we're going to go up 1 over 1, up 1 over 1, up 1 over 1. You can do it one more time. And then we will go ahead and draw our line through our graph. And what do we notice? Well, what I hope you recognized is these lines cross each other. And these lines specifically cross each other at the point 2, 1. The lines intersect, that's our math word we're going to use, intersect at the point 2, 1. Now, what's interesting about this is what if I wanted to solve these equations? What if I didn't have a graph? Well, we're going to get into that in later sections. What you need to recognize for now is when I graph two lines, where they intersect is going to be a very key point. Okay? So let's try another example. I want you to graph these following equations. Again, pause the video and graph them. And again, write down what you notice. AKA, I want you to look for where they intersect. Okay? Hopefully you've paused the video and done that at this point. If you haven't, go ahead and do it. For my equation in red, there is no listed y-intercept, so the y-intercept is 0. And this one tells me to go up 4 over 1 with my slope. I could also go down 4 and left 1 if I desired. And I'm going to draw my line through. Now we graph the other. This one's going to start at x plus 5. Okay, so I'm going to start at plus 5. And I'm going to go up 1 over 1. Probably need another point. Go up 1 over 1. And you'll notice that the graphs cross right in there. Okay? They cross right about there. Now, that's not really a nice, even, neat number. Okay? You're not going to find a nice, neat number. What, again, you should notice, though, is that the two lines intersect. Okay? If we graph this on a professional graphing system, I'll show you that here. On a site like Desmos, and we graphed our two equations, we could get the exact point of intersection. 4x and x plus 5. Let me double check that. I believe those were our two equations. And you can see we intersect here at 1.667 and 6.667. So sometimes lines don't intersect nice and neat, but the point is the lines do intersect. And I just wanted you to get some graphing practice. So you're probably sitting there going, okay, Mr. Carter, I know how to graph. Where are we going from here? Well, here's what 7.1 is going to be all about. When you graph two equations, where they intersect is the solution to the two equations. We never did the rectangle problem, so you don't need to think about that. But I want you to write this down. When you graph two equations, where they intersect is the solution to the two equations. Well, what do we mean by solution? We haven't really talked about that since chapter 2. Well, if you remember, the solution was the numbers I can plug in that make the equations true. The solution to an equation, if we go back up here, if the intersection is the solution, what that means is I can plug 2 in for x and get an output of 1. Okay, in this first equation, if the solution is 2, 1, that means I plug in 2 for x, and if I solve it, my y value will turn out to be 1. Again, what's cool about this is not only does it work for the first one, but it's the solution because it works for both equations. Again, for the second equation, if I plug 2 in for x, I get y equals 1. So when you look at the graphs of two equations, where they intersect are the x and y values that if I plug them into the original equations, make them true. So we've learned about how to graph equations of lines. And what we learned is that the solutions, sorry, I went too far, where they intersect is the solution to the two equations. When you graph two equations, where they intersect is the solution. Okay? So let's try this with a word problem. Mr. Carter decided to buy bamboo plants. After purchasing the plants, I'm going to figure out which fertilizer will help the plants grow best. Plant A is 6 centimeters tall and growing at a rate of 4 centimeters per day. Plant B is 10 centimeters tall and is growing at a rate of 2 centimeters today. We want to know when will the bamboo plants have the same height and what is that height. A lot going on here, but how could we solve this by graphing? Well, first and foremost, before we can ever graph, we got to set up some equations. Again, we haven't done this in a little bit, but always start with some form of total, okay? Or some sort of setup. Plant A is 6 centimeters tall and growing at a rate of 4 centimeters per day. Well, a lot of what we've seen so far is in slope-intercept form. So how we could think about this is what is changing and what is staying constant. Well, I know plant A is 6 centimeters tall. That doesn't change. It is always 6 centimeters tall. Okay? It grows at a rate of 4 centimeters per day. Well, that number is going to change based on the number of days, so I'll give that a variable. Let's call it D. And that formula, depending on how many days have gone by, will give me the height of my plant. Again, just kind of through reading the problem, we can set up an equation. We can do the same thing for plant B. Plant B starts at 10 centimeters. It's increasing by 2 centimeters per day. And that equation, depending on the number of days, will give me a height for the plant. You might be sitting there going, okay, Mr. Carter, we set up some equations, good for us. How are we going to graph with D's and H's? Well, just turn them into X and Y. If you remember back in chapter 6, we talked about dependent and independent variables. How do I know which will be my X and which will be my Y? Time is always going to be your independent variable. So time should be your X. So if I were to rewrite these equations, I would put x in for number of days and y for the height, because the height depends on the number of days. Do the same thing over here. Plug x in for the number of days, y for the height. And now I got some equations that I think I can graph. Okay? So why am I going to graph these? What's the point? I set up my equations. Well, we want to know when they're going to have the same height. AKA, we could tell this when the lines intersect. We're looking for the solution, and we know that if we graph our equations, we can find the solution. Okay? Given the information that they're providing me and how much I'm going up, I'm going to go by a scale of 2s. Okay? I'm going to go, actually, no, I'll go by a scale of 2s. Okay, so my first graph here, we can make this one in red. For plant A, we start at a height of 6, and we go up 4 over 1. So actually, what will probably make this a little easier is if we make our x scale go by 1s. We'll go up 4 over 1. Up 4 over 1. Up 4 over 1. Okay, now let's look at our green one. Well, we started at a height of 10 in our other plant, but this time we're only going up 2 over 1. Up 2 over 1. And what I find is that we intersect at the point 2, 14. So with our bamboo plants, we have figured out that the intersection based on the equations we created is at 214. So where do we go from here? Well, now we got to interpret our answer in the context of the problem. What is 2 and what is 14? Well, remember the x variable represented time. So when will the bamboo plants have the same height? At day 2. Again, that's our x value. That's where they intersected. And what is that height? 14 centimeters. Okay? How do we solve word problems? Well, they're just very similar to the solving equations by graphing that we did above. We just have to set up the equations here. Then we graph them. And again, the solution, where they intersect, is the solution to the system of equations, which tells us when they'll have the same height and what that height is. All right, let's jump back more into some typical graphing. I want you to graph these two equations. Okay, pause the video, give it a shot. So hopefully at this point you have solved it. If not, pause the video and finish. All right, check your work with me. So this equation, I'm going to start at +1. And according to the slope, I'm going to go down 2 over 1. Down 2 over 1. Down 2 over 1. Then I'm going to draw a line right through it. Now I'll do my other one. We're going to start at -1. Again, down 2 over 1. Down 2 over 1. Could even go the other way, go up 2 over 1. Then I'll draw my line. What you notice is these lines aren't touching, aka the lines are parallel. Okay, if you graph these correctly, you should have come up with parallel lines. So what is the solution? Well, if the solution is where they intersect, there is no solution. If you are ever graphing two equations and they never intersect, they are parallel lines. Now, I'm not talking ones that it just takes extending the scale to intersect. I mean, they are going the exact same way and they're not getting any closer together. The quick way you could have told this, by the way, parallel lines will always have the same exact slope, but they will have different y-intercepts. Parallel lines will have the same exact slope, but different y-intercepts, which usually means, if the lines are parallel, there will be no solution. All right, let's try graphing this one. Again, go ahead and pause it and try and graph this. Okay, I want to graph this equation. Well, you probably can graph the one in the green pretty simply. You go to positive 2. Slope's negative 1/2, so we're going to go down 1 over 2, down 1 over 2, down 1 over 2. Well, what about the one in blue? That's not in slope-intercept form. So that's actually in, flashback to chapter 6, it's in standard form. So there are a couple ways we could graph this. We could graph it using the intercepts. If you think back to chapter 6, we typically graph standard form by using the intercepts, or we could turn it into slope-intercept. Okay, I'll turn this into slope-intercept and then graph it. If you would like to just graph it with the intercepts in standard form, go for it. But I'm going to go ahead and turn this into slope-intercept form. What makes something in slope-intercept form? We got to get y by itself. Subtract 2x from both sides. I get 8 minus x equals 4y. Divide all sides by 4. And I get 2. 8 divided by 4 is 2. Minus 2/4, which is the same as 1/2. X equals y. Again, I've just manipulated the equation in standard form to have it in slope-intercept form. So now if I go ahead and graph this equation, my y-intercept's at 2, and I go down 1 over 2, down 1 over 2. And what you probably realize is it is the exact same line. One line on top of the other. Well, unlike parallel lines that have no solution, if where they intersect is the solution to a set of equations, and they are constantly intersecting because one's on top of the other, this would be an infinite solution. Infinite solution. Okay? The lines are lying on top of one another, which means they're intersecting forever, so it's an infinite solution. Last example. We're going to graph these. Again, go ahead and try it on your own. Well, if I plot my first one, I put a dot at +1. I go down 2 over 1, down 2 over 1, down 2 over 1. Maybe go up 2 over 1, or up 2 left 1. Connect them with my blue line. Now I graph the other. Start at -3. I go up 1 over 2. up 1 over 2, up 1 over 2, and I draw my line. Now you're probably noticing or looking at this going, oh great, the dots didn't match up. The dots did not match up. The solution is not a nice even number. And if we check it in Desmos, as we did with one earlier, if we check it in Desmos, negative 2x plus 1, and our other line was 1/2 x minus 3, we don't get a nice, even, neat solution. But the other thing I want you to notice is not only do these lines intersect at 1.6 and negative 2.2, but they almost create a little square. You see, what's unique about these lines is they are perpendicular. In fact, they intersect at a 90-degree angle. These lines are perpendicular. Now, how could you have told they were perpendicular off the bat? Well, their slopes, unlike parallel lines, are the opposite. Parallel lines have the same slope. Perpendicular lines, the slope is the opposite. Negative 2 over 1 versus the other one is 1 over 2. When slopes are the opposite, the lines will be perpendicular. Okay, so let's summarize all this information that I've given you. What do you need to know? Well, what you need to walk away from this lesson is hopefully a review of how to graph stuff in slope-intercept form. We're going to be doing that a lot. We also talked about how if we graph two lines and they intersect, that intersection is the solution to the problem. We saw some examples that had nice, neat numbers, others that didn't have very nice, neat numbers. Okay? So then we talked about, after we did a couple examples of getting our feet wet with graphing, and the intersection is the solution, we did a word problem where we had to set up the equations. But again, we graphed them, saw where they intersected, and that was our solution. Then finally, we looked at some special cases. What if the lines never intersect and they're parallel, and how can we recognize that? Then we looked at, well, what if the lines lie on top of one another? They're the exact same line, and what does that mean for our solution? And finally, we looked at how do perpendicular lines look, and how can we tell if they're perpendicular? Okay? I've summarized these special cases, the parallel, the identical lines, and the perpendicular lines here in these bullet points. So go ahead and finish the video up by pausing it right now and writing down these cases. Now you're good to try your practice. When you come into class, let me know how I can help you. Thanks.